Hello. Good morning. I hope that this is fun for you guys. My name's Phil. First of all, thank you for having me here. I'm pretty excited. I'm honored to be speaking to you guys. That you think that I know something is pretty cool. So hopefully you get something out of this. If not, get caught up on your emails and whatnot. So about me. My name is Phil Steen. I'm a director of IT services at 318. I've been there for 10 years now, I guess. We're an IT consulting company that's based in Nashville, or based in Los Angeles. I'm based in Nashville. I live there with my wife, my daughter. Because I live in Nashville, I'm a redneck at heart, so I enjoy four-wheeling and then also ruining perfectly good vehicles. And that leads to my next hobby, which is fixing everything that I've broken. So that's enough about me, though. We're here to talk about networking. So over the years that I've been in IT, I kind of Googled my way through a lot of stuff, setting up Linksys routers all the way up to doing large deployments now, learning about all the different devices and how to configure them. So I thought that when I was thinking about stuff to present on, I thought, well, my life would have been a lot better if I'd understood a lot more of this stuff earlier in my career. So I figured, why not share a little bit of what I've learned to hopefully help you guys. So we're going to do a little bit of fundamentals. It's a lot of data for a very short amount of time, so I apologize if it's a little bit extreme, but I tried to kind of get a 30,000 foot view of it. So the first thing we're going to talk about is layers. So you've seen a layer 2 switch, a layer 3 this, a layer 2 that. So what does that mean? So you've probably seen it when you go to buy a switch. You have an option for a nice $500 Netgear, which nothing wrong with it inherently, depending on what you're using it for. Or you've seen $5,000 for a Cisco switch and wondered, why would I pay that much more for a switch? Does the same thing, right? Not really. So that's kind of what we're going to talk about, is some of the reasons why you would want to spend that much more money on a switch. So when we talk about layers, this is what we're talking about. We're talking about the OSI model. This is a description of where networking happens and what happens at each layer. There's different layers of the network, different things happen at different layers, and we need to understand what happens at those layers to understand how to control, augment, increase performance for the network. We're really going to be talking about 3 layers mostly. We're going to be talking about data link, network, and the application layer. These are the ones that you're going to most be working with, so we're going to focus on those. We'll touch on layer 4 a little bit as well. There's another model to make things even more confusing, which is the TCP/IP model, which goes next to this. And so the world of networking is there's a lot of vendors, there's a lot of terms, everybody has their own way of saying things. So you have to kind of understand both models. So you'll see references in firewalls to application rules or layer 7 rules. You need to realize that that's the same thing. You'll see, see things called network access switches versus a network, routing switch. And so you can kind of see how it can be very confusing, but don't worry, I'll keep the layer thing up on all the slides so you won't get lost. So let's break this down a little bit. We'll break this down. I apologize for how much data it is, but we are recording, so don't go crazy with notes. So the first layer is that I'm grouping these together just because that's how we talk about them. Layer 5 through 7, we don't really separate those a whole lot when we're troubleshooting. When we're talking about it, it's just data. That's what we're talking about. An example of that would be web traffic, file sharing, DHCP, DNS, those sorts of things are all services that are sending and receiving data. The transport layer uses a data unit called a segment in the case of TCP, or a datagram in the case of UDP, which we'll talk a little bit more about later. And those are the 2 examples. You guys have seen those when you're working on a firewall. Pretty straightforward. Layer 3 is our network. That's where the packet layer's at. That's where we're routing things with IP addresses, whether it's IPv4, IPv6, IPsec tunnels. And layer 2, data link, that is our basic communication on switches. And anything that has an Ethernet connection is usually talking on layer 2. Most of the time, we're talking MAC addresses is the way that they're communicating and identifying one another. There are some other examples of that. We're not really going to talk about them, but LLDP is an interesting one. That's one where basically your devices can identify each other with layer 2 communication. They can send names and things like that back and forth. Pretty cool. So the physical layer. This one uses a bit. It is the most common one is Ethernet. It's the cables that connect everything. You know, the technologies like DOCSIS on your cable modem or DSL or fiber interconnectivity. Essentially, this is just binary communication, on, off, back and forth, electrical, light, one way or the other. All right, so let's talk about layer 1. So obviously there's Ethernet. That's the biggest one. And there's a lot of different versions of Ethernet. I'm not going to talk about all of them, but the new fun one that we like to put in wherever we can is Cat6a, 10 gigabit. Sometimes they're copper cables, sometimes I think they're starting to actually get now more flexible. The first ones used to be super like rigid, you couldn't even really bend them, but they're getting better. Category 6 is what you're probably going to run into at most current clients or your schools. 1 gig a second. Older places will have 5e. Be aware that 5e will do 1 gig, but only to a certain length. Once you're past that length, and it's published at 100. I don't think that's 100% accurate because I've seen 100-meter runs and they've gone down to 100 meg. So it really just depends on the loss and how many bends are in the cable and a lot of factors. But generally, when we're building a new network, unless there's a need for Cat6a, we're going to go for Cat6 because that's kind of the standard right now. But if you want to future-proof and you have the money, do Cat6a. Cat5, 100 meg. Don't use this. Just throw out all your Cat5 cables. They're no good unless you're really cheap, and like some clients I've walked into. Coax, you know, your cable provider, you know. Fiber optic, obviously. Again, these are all just for sending data on-off binary communication between devices. So layer 2, we have some examples here. We got layer 2 switches. So your basic switches that don't have layer 3, meaning they're a couple $1,000s more. You've got a network card. You've got a wireless access point. And the reason that both of the layers are selected is because as you move up in devices, the devices all have to do every other layer. So a switch has Ethernet ports, which are a layer 1 to layer 2 handoff. So because you're going from that Ethernet port to an Ethernet cable, that's also layer 1. So as we move up, we'll be highlighting all the layers because they have to do that as well. So let's sit and focus now on layer 2. So layer 2, we talked about frames. That's how the data is communicated by MAC address. How does that work? How are these devices identifying one another? How are they delivering this data in these frames? So we're using what's called Address Resolution Protocol, or ARP. I'm sure you're familiar with the command. You've probably run it troubleshooting sometimes. This is a protocol for matching an IP address to a hardware MAC address. So, you know, 192.168.1.1 equals ABCDEFG0001. It runs on every networking device. Your computers, your switches, your firewalls, everything that does networking on a layer 2 level is going to have an ARP table. And it keeps itself updated. There is also, they refresh. I don't remember what the refresh rate is. But there are times when you have to clear an ARP table because something's not working. You're like, okay, well, I just need to start over. Let's make sure that this works. And when you restart your switches, you're clearing your ARP table, or your ARP table. So when you have a network that's locked up and you reboot your switch and it clears the ARP table, that usually will fix it. And on switches, there's a separate MAC address table that link the MAC address to an Ethernet interface. So it's very easy to keep these two the same. They're not. So an ARP table will run on your PC. It will run on every networking device. A MAC address table is on a device that's actually switching these frames. So it links the MAC address to the specific port on the device where it's going to deliver those frames. So here's an example, and I've got my switchy 1500. So I've got, and forgive me if you guys don't know the reference of what I'm joking about, just bear with me. It probably won't be funny to you, but it was very funny to me when I wrote it. So we've got our switch, 3-port switch, you know, good technology. We have, I've kind of combined these. Like I said, it was confusing, so I made it even more confusing by actually combining them. So we have port 1, MAC address, IP address, port 2, MAC address. So you can see that these guys are up here in the table. So let me see what I'm talking about. So we say that Oyster wants to send a packet to Tane, perhaps a printout of Oyster smiling. And let's also assume that they've already communicated before. So there's an entry in their MAC address tables for one another. They know the IP address that they're at. So when Oyster goes to send this to Tane's IP address, he already knows his MAC address. So Oyster is going to wrap the packet containing the photo inside of a frame and send it to the switch. The switch, because it has record of his MAC address in there, is going to forward it directly to Tane. Easy. So that's how the network works once everybody's discovered one another. They understand who each other is. So let's say that there's a new person that comes into the office, salaryman. He hasn't been here before. He doesn't know any of the devices. This is his first day he's connected. He wants to send Tane a hat wobble. So we've got the hat wobble. Again, I'm really sorry if you're not getting this. It's probably really weird and bizarre, but anyways, I'm a weird guy. So he only knows Oyster's IP address. He does not know his MAC address. He's never been here before. So what he's going to do is send an ARP request out saying, hey, who has this IP? So he's sending an ARP. The ARP is going to go up to the switch here. The switch is going to say, hey, this is a broadcast. So we're sending this to every device on this broadcast domain. And you'll see that when it got that ARP request, the switch saw, hey, there's a new source MAC address. I've never seen it before. I'm going to add it to my table. Now I know that salaryman with this MAC address and this IP is at this port. So now we've sent the ARP out. It's gone to everybody except the sender. So the switch is smart enough to not send it back to the port that it came from to prevent loops. So both these guys have received it. Now, because Oyster is the one with the IP address in question, he's going to send an ARP back saying, I'm right here. Here I am. And he can send his GIF over to Oyster, or GIF, depending on which side of that argument you're on. So that's how it works when there's no discovery there. And like you see, it records it. Everybody else is recording it. I could have put ARP tables down here for these guys, but I didn't want to be excessive. So, all right, now we get into fun stuff. So virtual LANs. So I talked about broadcast domain. I just mentioned that. I didn't really explain it. What that is when you have a network subnet. So when you have a basic Linksys router, there's a 192.168.1.0 subnet. Everything on that device on that subnet is a broadcast domain. So a broadcast domain is really where devices are communicating on layer 2. Once we move out of layer 2 and we start to go to a different subnet, that is no longer the broadcast domain. So when we say broadcast domain, we're saying when they send an ARP request and it's going to everybody, who is that everybody? So what we can do with virtual LANs is it allows us to have multiple subnets on a switch. It allows us to separate that layer 2 traffic and limit the broadcast domain to the people that need to see it. So we're really minimizing the amount of traffic that's going back and forth on the switch. It's important to understand that with most switches, besides very expensive ones, inter-VLAN routing does not occur on that switch. It has to go up to another device to be routed to the other VLAN, even if those VLANs are on the same switch. So keep that in mind when you're designing this. It's useful for security, obviously, because you're separating those devices, and you can put rules in place at the switch or the router level that prevent them from talking. So these two VLANs could be completely independent. We see this a lot where we have a really nice brand new big network, and we've bought all these really fancy switches. And then the client says, well, hey, we've got all these security cameras, but we don't want people to be able to get on these cameras. So what we'll do is we'll create a VLAN for those ports just for the security cameras, and then we'll have a VLAN for voice, and we'll have a VLAN for computers, so we can kind of keep everybody separate. And we can build rules to prevent or allow access between these VLANs. By default, it's going to be allowed on most routers. But if you have clients that are doing MPAA restrictions and they say, well, your servers can't connect to these clients, and you can have these routing rules that are 2 pages long, so that's always fun. It does require planning and thought. So you don't want to just throw VLANs on there. You want to think about the fact that, okay, this data's got to go up and over and through a router of some kind to get between VLANs, and think about the performance hit. Okay, what are the links that are in that? Am I going up 10 gig to a 1 gig connection and now it's going to downspeed? So that's all stuff you got to keep in mind. So how do these work? So we've got a switch. By default, you take it out of the box, you turn it on. Every port on that switch is going to be a trunk port. So there's 2 types of ports. There's trunk and access. By default, just so the switch works, everything's a trunk port. An access port is a port that has only one VLAN. And to make things more confusing, you can have two, but for the purpose of this discussion, we'll talk about a single VLAN that is untagged, meaning it is the only VLAN on that interface. A trunk port, and again, this is where the manufacturer thing comes into play. Trunk is a Cisco term. I'm using that. There's a number of other terms for these, so bear with me, but I'm using Cisco terminology here. It enables you to send multiple VLANs up through that connection. So you can send multiple VLANs, not necessarily seeing each other, but they're tagged, so they'll be separated. And this is what we use to send VLANs up and down switches without necessarily putting it on that switch. And again, they can be tagged or untagged. And the way this works is the default VLAN on an access port, like I said, is untagged. So it is just, all the data going in there on those frames is just that data. There's no tag on it. A trunk port will have the primary VLAN untagged, so the frames that go through there will have no identifier on them. All others will be tagged. So if you have a trunk port that has 5 other VLANs, each of those VLANs, the frames that go through it will be tagged with the number of the VLAN that's going through it, so that the receiving switch can identify and understand how to send that data. And that's how, when we send these ARP requests on these broadcast domains, it knows to not send it to everybody because it says, well, this is only with this tag, so it's not going to propagate the whole network unless you have those tags enabled. And again, beware of the terminology because one that's I've noticed on HP and some of the other switches, they use a PVID to identify primary VLAN ID, and that's their term for untagged. So you got to do a little bit of homework before you can, on your specific model, before you can jump into this. So let's do a picture of this. So we've got our trunk ports here. These are our inner links between our switches. These are how our switches are connected. We have these two ports are trunk ports for 1 and 2, and these two down here are only on VLAN 1. And right here you've got your key for the VLAN. So let's say VLAN 1, we have an access port up here for, these are all going to be our phones. So these ports here, access ports, configured with 1 VLAN only for our phones. You can see they're traversing the switch on the trunk port because we've got 1 here and we've got 1 here. So that's how that VLAN is making it down to these other 2 switches. We've got another VLAN for our computers, VLAN 2. So we've got an access port here, an access port here. But we can't enable this VLAN on the switch. Well, we can, but it's not going to work because we have not sent that VLAN down here. That doesn't prevent you from turning on VLAN 2. So you could set one of these ports as an access for VLAN 2, but no data is going to make it down from the top of the network because it's not allowed to. All right. Hopefully that was exciting. This is good stuff. All right, so layer 3 plus. I'm going to kind of break it up a little bit here because when you get to a certain level, the devices all do everything. So layer 3 is our routing layer. This is where we are taking destination IP addresses and passing it off to the next device, the next router, the next switch, so that we can pass it along the network to the destination. Because all these devices are going to include Ethernet ports, they're also layer 1, layer 2. And the reason I've highlighted all of the layers here is because a nice firewall will do packet inspection and do application level rules. So layer 4. This is the TCP UDP we talked about before. There's a couple different protocols in here. We're really only going to talk about TCP UDP because those are the ones that we use mostly. So TCP is connection oriented. So this is a two-way communication between hosts. There is a discussion about setting up the session, and then there is the actual data transfer. And there are means for checks and balances. So when the receiving host doesn't get all the data it's expecting, it can ask for it to send more. So there's a communication about the quality of the data going back and forth. It has flow control. So because they're talking, you can say, hey, wait, I'm not ready. Slow down. Give me some time. It is slower than UDP because of this checks and balance method. And when I say slower, obviously, that's all relative. And we use this where data integrity is of the highest priority. So we want your web page to load correctly. We want your file to get to you, not in pieces. UDP, connectionless, one-way push. There's no communication. It's just sent out, hoping that the recipient is ready to receive it. It is obviously faster than TCP because we don't have this communication. It's just a blast. We use it where speed is the highest priority. So it's important to understand that this isn't a choice. You don't have a choice. You are using whatever the software architect has designed for their communication method. And it's important to also understand that some services use both. So for instance, voice over IP uses TCP to create a call connection and signal the phone to talk because there's a communication back and forth about that call. The actual voice data is just UDP because it's a stream. We don't have time to check it or we're going to have delays on our phone. So we have to just send the data, and that's why when you're on the phone and you start hearing that crackle and dropping out, that's your UDP stream getting interrupted. So more simply, TCP is a package with the destination delivery. There's tracking. You can see where it's going. UDP is a catapult. It just throws data, hopes somebody's there to catch it. So layers 5 through 7. I'm not going to really dive into this too much because there's a lot you can talk about with this, and I don't think that most of us are probably going to be getting into this layer. You're already doing this. This is the application layer, which I think is a super appropriate name because you're generally troubleshooting it in your operating system at the application level. You're looking at, why is my database not connecting? Other than basic IP, is there a misconfiguration in my software or something? Examples of this, like we talked about before, web services, file sharing, DHCP, DNS. These are just services that are set up to do this communication. All right, so now we talk more about manufacturer nomenclature. So these terms get thrown around a lot, and I wanted to kind of talk about what each one means. So routers, firewalls, security appliances. Routers, it's pretty rare nowadays that you see just a router. Unless you have a very large organization that has an intranet that's using routers at head ends and they have dark fiber, you're not going to see a lot of routers. Most of them are routers / firewalls. They're multifunction devices. But the purpose of a router is to direct traffic between local subnets, the intranet, and the internet. And it does, some of them have basic firewall functionality, so you can block specific subnets and specific ports. But they're not really as advanced as a firewall. They don't have the advanced functionality that you get on a firewall. So firewalls also work on layers 1 through 4. Controls inbound and outbound access based on a rule set. It's really a router plus you can have a little bit more advanced control. And my favorite, security appliances, next generation firewall. And I'm just going to call it next generation firewall because it makes me happy. That's my favorite term for it. So it's an advancement beyond, I think it's the most appropriate term because it's an advancement beyond a generic firewall. You can do things like geographic restrictions. You can do things like deep packet inspection to control access. You can make decisions about blocking specific services based on your company's needs or slowing down some services or guaranteeing speed for some services. Content filtering is another one that most next generation firewalls will do. And a lot of these are not, a lot of them, you buy a firewall and then you pay for a license for next generation services. So a lot of devices are already ready to do this, it's just a license. Like SonicWall's notorious for this. You buy a NSA 240 and then, oh hey, you want security services? Give us $1,000 for this 3-year license and you're good to go. So I would just say that, in the small, medium business world, most things you're going to run into are going to be a router / firewall. It's a combination device. Schools, bigger organizations will generally have a security appliance. They may even have a separate router and a separate security appliance. It just depends on the needs of the organization or what it thought they were doing when they set it up. Yes? Yeah. Which do you recommend? I'm a big fan of devices. Oh, I'm sorry. Yes, I'm sorry. So the question was, you can do, yes, the question was about software versus hardware for security appliances. Yes, you can set up a box and install PFSense or whatever you want to run a firewall, run a next-gen firewall. It depends on your budget. Like I'm a big fan of having a manufacturer that I can call and harass when something's not working. because I don't want to be an expert on everything. So, you know, I'm going to call the vendor. Again, it depends on you know, what you need. There's certainly more to think about with the software. You've got to have, you know, spinning disks or SSDs that run it. You've got to maintain that system's health. You've got to be aware of, you know, specific vulnerabilities that come with that software. You know, when you buy a Cisco or a Meraki or whatever, that's their job to figure it out. You know, you just put the box in. Obviously, the boxes are going to be more expensive, you know. And some of the vendors will not publish their specs. You don't know what their processor spec is. So you got to base your decision of what you need off their white papers, you know. So yeah, I mean, you can do it both ways for sure. All right. So now let's talk about encapsulation. So I've kind of touched on this a little bit, but this is an important thing to understand as you troubleshoot networking, because you need to be able to understand what these different levels look like inside of a network as data moves through the network devices. So let's say that you have someone special in your life, like Bill Smith, and you wanted to send them a rubber chicken. So that's going to be our data. That's our 5 through 7 layers. You're going to go ahead and get that ready to ship. You're going to package it in a box. That box is our transport layer. That is how we're going to be moving this data back and forth. You're going to take that to the post office. You're going to put it in a truck. Or they're going to put it in a truck. You probably wouldn't do that. I think there's law against that. That's going to be your layer 3. These guys are determining where this is going. You know, it's going to change hands a number of times before it gets there. It's going to go to, you know, one post office switch trucks. It's going to go to a distribution center switch trucks. It's going to go to the end post office and get put in a small mail truck. So that's your layer 3. We're routing this through the internet. And it's important, just think about the fact that every time it changes hands at one of these distribution centers, it's getting unloaded, so taken out of the truck, handed to somebody on hand, put in another truck, and moved on. So we get this picture of kind of almost unwrapping and rewrapping, putting different layers on the outside of this item as it travels. So ships off. Data link layer 2. So we arrive at our office. The mailman gets out of the truck. He's got it in his hands. He knows the mail clerk at this office. So they know each other. They have a relationship. He hands it to the mail clerk. The mail clerk says, oh, hey, I know this is going to Bill Smith. I'm going to walk this down to Bill's office and hand it to him, because he knows where Bill lives. He knows Bill's port, if you will. So more specifically, and this is, it's really hard to explain when you try to explain it in words. But so original item we have here is our data, the actual stuff we're trying to get back and forth. When that hits the transport layer, and this is done by your operating system before it starts to put it out your NIC, it's put in a UDP wrapper, if we're doing UDP, and this would also say TCP if it's TCP. But so it's put inside of that. Then when we get to the layer 3, it's put inside of an IP header. And then when it gets to the layer 2, it's put inside of a frame to go between layer 2 devices. And it's important to understand that when each device receives this, it unwraps it to those levels. So the router, when you're sending out to the internet, is going to receive this item, unwrap it to the IP, and because it's a layer 3 device, okay, I know where this is going. Rewrap it in a new IP header, send it to the next device, back in a frame to the next device that's on the route. So it's kind of this constant unwrapping, rewrapping. The source always stays the same when we're talking about on the IP layer. So the source IP address is always going to be the same unless you traverse a firewall. If you traverse a firewall, it changes it for you. And that's so that the data can find its way back. That's why that works. MAC addresses are going to change from device to device. So we have one device that sends it here. It's going to set its source and its destination, and then the next one changes its next one so that it can route correctly wherever we need to go. All right, so that was a lot of basic stuff. I mean, that stuff you learn, we'll talk about it, but you learn that stuff in a book that takes like 3 months to read, so it's hard to explain it in a few minutes. So let's talk about some network designs. This is your traditional home small office network. Linksys or a Cisco. I had the Cisco stencils handy, so you're welcome. This is a single device performing everything. You have routing, switching, and wireless all happening on one device. We're asking one device to do all these things. All that processing is happening on one processor, or two, depending on the device. Most home devices are going to have one processor. And the LAN is a single broadcast domain. Everything behind that firewall is on one subnet. Pretty straightforward. You know, some of these devices you can configure multiple subnets. You can do more advanced things, but it just depends on the level of the device. Let me go back really quick. So this one, this is like, you're going to see this for people that are home office people, remote offices that have a couple of staff, very small organizations. So small and medium, I'm saying here 15 to 50 people in the office. We have more independence here. We've got network functionality split between a router, a layer 2 switch, and a wireless access point. And the LAN is still a single broadcast domain in this environment. And it doesn't have to be, depending on your router and your switch, but when I'm talking about this, what I usually see. So all these devices are still, and these are the ones you walk into where the owner set it up. He's like, oh, I know computers. I've got a switch, I've got a router, and here's my WAP, and it's all just plugged in together and it works. So large network, this is where we're getting the more fun. And that's my identifier for next generation firewall. I hope you like that. I'm a Star Trek nerd in case you can't tell. So this larger network, let's focus on this for a few minutes. So this is somewhere where we're talking about 100 plus employees. There's going to be a much more thought placed on performance, security, and fault tolerance, right? So in this example, we've got 2 internet connections coming in. So we have a backup and a failover. And it didn't show up well, but that's the one from the IT crowd. So thank you. It's the internet, Jen. It's wireless. Of course it's wireless. So yeah, I should have put a wireless connection there. That would have really committed to the joke, but I didn't want to confuse anybody. So, so with this next generation firewall, and I kind of wanted to play the theme song every time I said that, but I thought that would be too much. We've got 2 internet connections, so we can make decisions as a business about what we want to send over which connection. This is also for fault tolerance. We can have one fail over. I mean, most of you guys probably have places that have more than 1 internet connection. That's pretty standard now. But with a next-gen firewall, you can say, okay, anything that is network streaming, video streaming, I want that to go over my backup connection because I don't want people watching Netflix and hogging up my main pipe. You can aggregate them. You can say, I want to use both of these. And it's not going to be 1 plus 1. It's going to be a combination of the 2. But people always think that, like, well, we got 2 100 bank connections. We got a 200 bank connection. I'm like, no, that's not quite how it works. You can do, on this device, we can control and say, well, you can't do any peer-to-peer file sharing. You can't use, what do you call it, a LimeWire or whatever the kids are using these days. I like on my firewalls, there's a button, block peer-to-peer, and I just turn it on. I don't have to worry about it. And then they update it when there's a new one. Below this, we've got our core switch, which is essentially a router. Because routing, and we'll get into this more, but routing for this network is actually happening at this level, not at this level. We are not asking this firewall to do routing. We are asking this firewall to do firewall duties and packet inspection. We're reserving those processor resources for that so that we're not taking a hit on our internet performance. This core switch is connected to another switch over here, which could be a layer 2 switch for our server rack. And this would be, I didn't really identify this, but this would be 10 gig fiber. And anywhere you see these little dots here, we've got redundant links. And we're going to use what's called RSTP, which I can't remember what it stands for. I had it written down somewhere, but that will shut down the unused link so we prevent a network loop. Because if we had a layer 2 broadcast domain connected twice, we would have a loop of data going back and forth, and it would eventually lock up the switch. And sometimes when RSTP fails on a cheaper switch, you'll see that happen. And that's where you get all the lights just locked on and the switch not doing anything. So we only have one active connected at any given time. These switches here are connected with a loop here. But internally, they're a stack, so they've got stacking cables on the back. So these switches actually present as one switch when you're in the admin interface. Ports 1 through 140 something. So it's a big switch stack. And those backplanes are usually like 40 gig. It just depends on the model. So you kind of get a lot more throughput. You're not dependent on a 1 gig uplink between switches or a 10 gig uplink. You can really get the data transferring well between them. And you'll see that I've also got a redundant link there. So these are looped together. And if there's a failure, like this switch fails, it's going to switch over so you don't lose your whole network. That's the whole point of this, is you're still going to lose a switch. We can't really protect against that. But what we can protect against is one switch failing and taking out the whole network. You'll lose some clients, but you won't lose everybody. That's the whole point of that. Also on this, let me see if there's anything else to point out before we move on. Okay, so we have our VLANs. So this is a larger network. We're going to separate all this stuff. So this is very topical, but we've got a separate VLAN for our servers. We want to separate them. We've got a VLAN for wireless clients. We've got a voice VLAN. We've got a computer VLAN. And these obviously are traveling down the trunk ports here that we've configured. And we're setting access ports for the devices. What we'll talk about a little bit more is, okay, well, if this is a separate subnet and these guys are going back and forth to this, what are the performance implications to that we need to think about? So we'll talk about that a little bit more, but something to think about. So with this setup, we've got a separate firewall, we've got a separate router / core switch, and we've got separate access level switches. So this gives us a tremendous amount of control over the network, and with great power comes great responsibility or whatever, right? So we've really got to think about this. So let me just break this down a little bit more just so you understand. So this is something that caught me off guard because I hadn't really worked in these environments when I first started doing this. A separate network exists because essentially if you're thinking in small business terms, this core switch down, this is your network that you're used to seeing. This is your router right here, right? We're adding this security appliance here. So this is actually a small subnet that's just for communication between these two devices. These clients don't see this router. Like if you were to go and look at a Bonjour Discovery the network, you wouldn't see this firewall up here. You're only going to see this switch. This switch is your DHCP server. In this instance, this switch is your gateway. So you have these interfaces. So devices that are on this subnet here, there we go. Devices that are on this subnet here see this is their gateway. Devices that are on this subnet here see this is their gateway. Devices that are on this subnet, and so forth. So this core switch has multiple interfaces depending on which VLAN subnet you're on. And then the actual outbound internet, the only traffic that's going up here is either management traffic for my admin workstation or internet traffic. Everything else stays on this little environment down here. All right, I bet you're really excited for this graphic. I didn't do one because it was going to take too long. And it would be way too small to show on here, but well, I want to talk about, it doesn't differ a whole lot from what we just saw. There's just more of everything, and there's some different considerations. So we're even more concerned with high availability and redundancy. We're going to have things like hot standby router protocol or virtual router redundancy protocol, which allows you to have two routers, firewalls, next-gen firewalls, whatever you want to call them, sitting next to each other. One is in off mode. It's just kind of soaking up the configuration changes. And then let's say the primary router just dies, power supply pops. That second one just takes over. And the clients know no difference because it's configured to look like that device, and all of its network connections go active all of a sudden when it's there. It's already been connected to the network. So switches. So we're going to have higher end switches. We're going to have a core networking layer that is fiber-based as opposed to having all Ethernet-based. We're going to have a core switch that connects all of the lower switches in the network closets via fiber. So we have this kind of fiber backbone connecting, and that kind of keeps your speed up. We don't want to have 15 links of Ethernet to get to the main network. Multiple connections through RSTP, so we're going to have redundant links going to every network closet, and there's going to be a loop on every one that's disabled automatically by RSTP. That gives us failover capability. And we're going to distribute the workload across all the devices. We're going to have a separate firewall. We're going to have, maybe I have yeah, here we go, sorry. Dedicated routers, firewalls, content filters. These are all, in large environments, there's going to be dedicated devices, and you're going to have teams or a person that is your routing guy, and a guy that's your firewall guy, and a guy that's your switch guy. And that's just, when you're talking about big organizations, that's just how it is. And then we'll also have, in many environments, a corporate wireless network that has a controller that controls segments of the network. So you'll have one building has a controller for all of its wireless devices. Or you could be smart and get Meraki, and it's controllerless, but that's another pitch. This is a big one that I've found that is super helpful. Separate management VLANs. So when I set up a network, I like to set up a default VLAN that is just for management interfaces on all of my switches. And the reason I do this is because, we'll talk about this later, when you're VLANing, if you accidentally hit the wrong VLAN, you've just lost access to that switch you're messing with. So it's always good to have a separate VLAN that does not ever change, and it's just your management VLAN for all your devices. And it also separates your management traffic, so people couldn't inject and get passwords and things like that. It's a separate traffic flow. All right, so network design. This isn't a client that I saw, but I found this picture and thought it was appropriate. But I've seen worse than this. So plan ahead. The biggest thing with networking is to really think about it. The worst networks I worked with were people just went and bought stuff. And they're like, oh, we need some switches, we need some cables, we're just going to throw it all together, it'll work. Plan ahead. Build yourself a nice network map. Get OmniGraffle if you're a Mac person. Visio if you're a PC person. Consider the subnet scheme, okay? In a larger organization, this comes into play because you can do subnet rules based on like a group of subnets. So you can say, okay, this section of the office is going to be this subnet, and then you can make a smaller rule that is a larger subnet and say that blocks this whole section of the building, even though they're separate subnets. Consider your bottlenecks. Think once you've got your pretty graph where data is going and what kind of data is going where, and think about the least common denominator. Like what port is this going to hit that's only 1 gig or 100 meg? And what's that going to do to my traffic? Is that going to limit everything? And account for growth. And these these two are kind of antithetical, but you know, you want to balance planning for the future, but also not going crazy. Like I walk into clients where they've bought, you know, all Cisco super expensive switches, and they just don't need them. And it's like, yeah, that's great, but now you got to pay me, you know, twice what you'd pay somebody to do a normal switch, you know, or just get a basic dumb switch for your really small company. Don't get a layer 3 switch. You know, it's a balance. You got to figure it out because we're tech people. We like to have control. We like to add these things, but you know, don't go crazy. And again, document. So this network map that you built, document it, update it, keep it up to date. So if you get hit by a bus, somebody else can take over for you. And what's also important on these is like on these network maps, map out your ports, like write down the interfaces, write down the management interface, write down what port is plugged into what as far as the uplinks. Now I don't really care so much about the individual ports because those are more fluid, but I want to know what link is going to where on my switch. So bottlenecks. Again, consider your limiting factor. Consider the routing between subnets and VLANs. Where is that happening? How is that happening? What kind of links? Consider the network device backplane performance. So what is my switch stack? What is the backplane of that switch stack? How is that, how fast can that communicate? And that's one of the advantages of stack switches is a lot of time it's much faster than connecting switches with gigabit. Device connection speed. So this is another one. Don't overlook the fact that if your network is 100 meg, you've got Cat5 cables in the building, a gigabit switch isn't going to do anything for you other than maybe make your server a little bit faster. It's not going to really do a whole lot. If you've got bad wiring, you've got bad wiring. The best switch in the world is not going to help that. Although Cisco now has a new thing which is called multi-gigabit, which is like 2.5 gig over Cat6, which is kind of cool. I don't know how real that is. I haven't tested it yet. But all right, so graphically, we've got here a nice little network. This is our very enterprising young IT person set this up. We've got all these nice Cisco level 2 or layer 2 switches. We've got a layer 3 firewall. There's a Cat6 connector going between them. And because he's a good IT person, he's like, man, I really want security. I've got VLANs for all my computers. I've got VLANs for my phones. I've got VLANs for this department and that department. There's 15 VLANs on this switch stack. That's great, but because these are just layer 2 switches, all that data is going up and over this Cat6 to get between VLANs. So when your client goes to connect to the 10 gig connected server, he's only going at 1 gig, and you've got 15 other people going at the same time. This is your bottleneck right here. Now, consider that, and then look here. We've got our nice layer 2 access switches with our 15 VLANs, but we've got a 10 gig fiber uplink to a nice big aggregation switch. So this is our routing switch. So this is doing all the routing, and this is doing it at 10 gig, right? So we can hook our servers into this at 10 gig. Our clients are down here. They can connect over 10 gig to the server, if they have 10 gig, obviously. But we're thinking about aggregation here. So you've got 10 clients at 1 gig trying to connect to the server that's 10 gig. You'll get better throughput, right? And the only thing, again, traversing this is internet. We're not sending everything up and over to the firewall. We're really asking this switch to use its processor resources for routing. We're keeping this thing free to do its internet business. And there's our bottleneck that I was so helpfully pointed out for myself. All right. So how do we apply all this? What are you guys doing every day that we can kind of take this and apply it to? So one of the most common things you're going to get asked to do is I need you to open a port on the firewall. I need you to open it to the internet. I can't get to this server from home when I'm supposed to be working at the office. So port forwards are opening a hole in the firewall. And there's a lot of terminology here. Again, different vendors, different things. But for the most part, it's pretty consistent. Port forwarding is using a single public IP address that is assigned to the router only, so the router's IP address, and directing data by port. So the user goes to that server, they hit this, or that router, they hit this port, and they get directed to this server. And if you go on another port, you're going to a different server. This is a little limiting because if you have more than one more than one web server, more than one email server, that's not going to work. You need more IP addresses. So that's where NAT comes in. NAT is network address translation, which is using one of several public IP addresses you have available to you other than the router's IP. The router's IP, we generally are using port forwards, but NAT is tying one public IP address to one server. This is a one-to-one NAT, so one public IP to one server. So that's why we call it one-to-one NAT. You can limit the ports on this. So you can also set the ports, and that's more of an access rule than anything. It's important to understand that this one-to-one relationship is by IP, so it's IP to IP. The actual ports are more an access thing. We say, oh, we're only allowing these ports, whereas with port forwards, you're actually routing by port, so it's a little different. We have one-to-many NAT, and again, it's not called on everything, so everything does it a little differently, but as long as you understand the meaning of it, you'll kind of figure it out. One-to-many NAT is a combination, which will allow you to use a same public IP address, again, other than the router's public IP address, for multiple internal destinations and direct it by port. So you can still use that same IP address on multiple machines, but now you can add the port routing. So let's graph this because it's kind of hard to explain. So in this example, we've got a router that has a single public IP address. So there's our WAN IP of our router. We've got a LAN IP here, and these are our LAN IPs of our servers, right? These are our rules. We're just doing port forward here. So we've got port 80 going to server.3, and we've got port 25 going to the server. So user 1, and I hope you enjoy, these are my Cisco guys. Isn't that great? These are the Cisco pictures. I love these. They're so cheesy. So this guy's opening an HTTP connection from the outside, from his home office where his cats are probably sitting in the background. And so because of this rule here, 80 to .3, we can see he's hitting on port 80. The router's saying, OK, you're coming in on 80 on my IP address. I'm going to send you to the server. Guy 2, he's a dog guy. He's going in to send his mail. He's connecting on SMTP, which, another thing, please don't open 25 on your, this is just for an example, but I should have used 587, but you know what I mean. All right, so he's going in on 25. He's getting directed by this rule for port 25 to go to server 2. Simple enough. That's port forwarding. And all these are using, again, this IP address only, no other IP address. One-to-one NAT. We have our same WAN IP for our router. That hasn't changed, but now we've called Comcast. Sorry if there's anybody from Comcast in here. And we've gotten our upgraded IP package. We now have three public IPs. So we've got one for our router, we've got one for our, one for one server, one for the other server. And we've got 2 mail servers and 2 web servers in here. So user 1 is opening an HTTP connection to this WAN IP. So this is the WAN IP for server number 3. So we are seeing he's hitting this rule. He's connecting to this by IP address. These ports are allowing him through because we've said we allow 80 through, but that's not how the actual routing is happening. It's happening based on IP address. He's opening an SMTP connection, again, unsecured, stupid, on this public IP .2, which is affecting this rule. Again, by IP address, not port, but we're allowing him through because 25 is allowed. And then he's now connecting to port 25 on .3, and we can see that directs now because he's doing it by IP address. The port doesn't matter because we've got rules for different ports. All right, one-to-many. This one's more fun. So we have the same WAN IP of our router. We have now we still have the same number of public IPs, but we've added a new server. What do we do? What's going to happen here? So now we have this VNC. I don't know why I picked VNC. That's a really strange port, but whatever. This is our Mac server, and we're going to remotely administer it from our little small workspace here. So we've added now, we have 2 servers at this public IP address. So the .2 public IP address now has 2 servers. But you'll see one is 25 and 80, one is 5900, and they go to different servers. So this guy, he's really web browsing. He's going to .3. And we already have a rule for .3 on 80, so we're going right there. Now we're hitting this duplicated public IP address now. So he's hitting this on 25, so he's going to go to this server because we have a rule for 1.2, 25 goes to .2, so there we are. So now he's also opening a VNC connection because he's a power user. So he's got this VNC connection going into the router, which is the same public IP address. So the router is looking at this and saying, okay, I've got actually 2 entries for this. Which one are you after? 5900? Okay, you're going to this server. Okay, so we talked about VLANing and how exciting they are. On Cisco and similar architectures, on anything you touch, back up the config before you touch it. It's just a good practice. Like, before I get on a Sonic wall, I'll download the config. I'll make the backup config so I can just reboot it back up before I screw something up. I should go back to that. So on the Cisco ones, there's a cool thing. So don't write your startup config until you're sure that your config works. Because then you can call the customer and say, please reboot that switch. I made a big mistake. And it will come back up the way it was. Assuming you wrote the startup config before you made changes, because the last Cisco guy may not have. That's always a fun one with Cisco, is if you forget to write your config. Remember that when VLANing a network, you need to enable the trunk ports from the bottom up. So let's say you've got 3 switches, and you want to add a new VLAN on this bottom switch that hasn't existed before in the network. You've turned it on the router. You've got a new subnet going, a new VLAN number. So you've added this access port, but it's not going to work because it doesn't traverse the network. So you need to go up to the uplink port of that switch, add that VLAN to the trunk port, go to the up, and work your way up the trail. And this is why a network map is good, because you can see where the trail is, and allow that VLAN on those trunk ports so that it will travel the whole network to that final access port. And when you're doing that, don't forget the redundant links, because the worst thing is if you've done all this and then one switch fails and your network falls apart because you haven't added those VLANs to the redundant links. And again, this is where it goes back to when I set up a management VLAN. When you're editing uplinks and trunk ports, be very careful that you don't monumentally screw things up by taking out your connection. That's especially true on Cisco firewalls, where there's a deny all rule at the bottom, and if you get it out of order, you'll cut yourself out of your own firewall. Can you please reboot that for me? So here's some stuff that will be helpful, I think. I do a lot of, like I said, I live in Nashville. My company's in LA. I don't go to clients, so everything I do is remote. So I've kind of gotten good at figuring out where people are on a network just by going through devices and tracing them. So let's say that a customer calls in. They're getting a weird IP address. Well, oh, you must be plugged into the voice VLAN. Well, okay, well, this is my new desk. I need to get set up for this. So, we'll get you switched over to the data VLAN. So find out their IP address. What's your current IP address? I can then go into the switches, switch stack, whatever it may be, and look through those switches until I can find that IP address somewhere. And I can trace it through the network until I get to the correct switch. I'll look at the ARP tables. I'll then look at the MAC table. Once I've found the correct switch, I'll look at the MAC table, and I can see, okay, they're actually in this physical port. So I can then edit that config. But remember that a port that has multiple MAC addresses on it is likely a link to another switch, because the switch doesn't know what's on the other side. It just knows who's there. So when 15 clients on this other switch send data up through this uplink port, that MAC table is going to have 15 MAC addresses there. So if you're trying to find a client and you see one that's got 15, that's not the one you want to edit. You want to go further, get on that other switch that's on the other end of that connection. Another thing we do, telnet to see if a port's open. Obviously, this is TCP only because it's what? Connection oriented. So UDP is never going to respond to you. Don't try. There's a joke, right? What is it? Did you guys hear the joke about UDP? Did you guys hear the joke about UDP? Did you guys hear the joke about UDP? Thank you. I'm here for the next 20 minutes. What else we got? So this is a good one. As you get more advanced in this, and you're working with vendors, and your VoIP vendor's like, you know, you're something wrong with your network. Your phones suck, or your network sucks. Our phones are perfect. You can say, let me do a packet capture. Let's figure out what's going on. This is a cool thing that a lot of nicer switches will do, which is allow you to take one port and mirror that traffic to another port. So what you can do is get your Mac or your PC or your Linux box, start up Wireshark or another packet capture tool, plug it into this mirrored port, and obviously you're not going to get a network connection because it's just showing you the raw data from the other port, but you can then run a packet capture of that phone without interrupting that phone. That user can still make calls and you know, have problems with their phones, and you're catching all this, and you can send it to the vendor and say, here you go, here's a packet capture, tell me what's wrong. Or you can really get adventurous and look through it yourself, but let's see. Here we go, this is a good one. Internet's down. What do I do? My client calls. I'm in Nashville. They're in Chicago. Internet's down. What do we do? Well, that's a good one. But before I tell them to reboot anything, I like to see if I can hit the router admin. Or if it's a Meraki, you see I like Merakis, you can check the admin page, see if the network is down, see if the device is offline. If you can hit the router, we know the internet's good. If the router's up, get in the router. Depending on the model, it should have a ping functionality. See if you can ping some devices on the network. See if you can ping your switch management interface. See if you can ping your server. Figure out, and again, if you have a network map, you'll know where the network is broken. Oh, this switch is offline. Can you check the lights? Yeah, they're all solid. Okay, reboot it. The ARP table probably filled up. Again, work your way through the network until you find the problem. So another fun one, the internet's just really slow. I don't know, you know, I can't, files copying to the servers is really bad. The internet's slow. Well, the server's on your local network, so it's not the internet. So on your switches, routing devices, look at CRC errors, so cyclic redundancy checks. Most good switches will, on every interface, keep a counter of the CRC errors. You can reset these. I don't know if they have a cycle. I think they're a lifetime cycle until you reset them. But if you see an interface, let's say you reset them and you let it sit for an hour and you come back and you check, and this one port has 50,000 errors and the other ones have none, you've found that probably a bad cable, a bad network card, something like that. Another thing, if you know this network really well, you know that everybody's wired in with 1 gig. They got Cat 6 to every workstation. They have a separate voice line because they listened to you when you told them to do that. Look for a bad link speed. So you can even do this on the front of the switch, depending on the model, but you'll see the lights of what color the link is. But most of them will give you a graphical interface of the actual ports of the switch, and it'll tell you the speed, or they'll give you on a Cisco a list of the ports and the current negotiated speed. Look for something that's been downgraded to 100. If it's not supposed to be downgraded, you may have a cable issue. I've had bad cables cause this a number of times. Even previously good cables, somebody ran over it with their chair, and now it's negotiating at 100. iPerf. So iPerf is fun. I think it's made by a French guy. I don't remember his name, but it's pretty old, but it still works on the Mac. You can find it packaged. If you get it from him, you have to compile it, but there's a guy that packaged it, and I usually install that one. But this is a software you install on one device. You can use a server at the client, or you can use, when I'm setting up a new network, I carry a separate MacBook, and I run, I'll plug in the server room. So what iPerf lets you do is it's a command line. You can start a server running on your device, whether it's a server or your MacBook plugged into, say, the core switch or the top of the network, right? And then you can take your laptop and run iPerf tests to that IP address from everywhere in the network. I'll go to each switch, I'll record it. I'll go to each access point, make sure I'm on the right access point, record it. And that way you can see, it's literally just copying a file and recording how long it takes. And you can compile this into a spreadsheet and look and say, well, this one switch has got a bad connection. So you know that you want to troubleshoot that switch. What's going on with the links? Is there a problem with the links? Is there a weird VLAN issue? Did somebody turn on some function on this switch that I don't know about? This applies again to troubleshooting and a new network. I do this with every new network. I just walk around and make sure that I'm getting the speeds I would expect to get, make sure I don't have a bad cable from a vendor or there's a bad switch, something like that. Because I've had issues as weird as half the switch is slow and half of it's not, and it was a backplane issue. They had to replace the switch because the actual components inside the switch had a problem. Okay, so this is the other one where I'm just going to hide if there's anybody from Comcast in here. Just kidding, I have Comcast at home, it's great. So rule out your local network first, and they will love you for this. Do not call them saying that your wireless is slow when it's not their problem. And if you tell them, hey, I've already done this, a lot of times they'll skip over their whole spiel, and it's great, and they don't read through the script. You say, look, well, I've already done this, I've done this, and this, and they'll just skip it. So check out for port flapping. This is bigger on enterprise providers, not your cable providers, but like something like Telepacific or whatever, a T1 provider. A lot of times when you get your device and you plug it into the WAN connection, it's just going to go to auto negotiate. And a lot of devices don't like that, and they want you to be set to 100 full. They want you to be set to something. So always ask the ISP. Say, hey, what do you want this set to? Because I've had internet speed issues caused by that negotiation just going back and forth continuously, port flapping. So ask them. If there's ever a question, just say, hey, are you guys seeing any flapping on your device? Do you want me to set to a specific speed? What do you recommend? And if they say no, then great, leave it on automatic. But when you're running your speed tests, so let's say you've ruled out your local network. You've done iPerf testing. Everything's great on your local network. Make sure that you're plugging in directly to your router or directly to the actual internet when you're running an ISP test. So don't complain that pings are dropping when you're connected from a switch on the other side of the building. Go and plug into the router and test that and prove that it's the internet if it's the problem. I usually just ping 8.8.8. I mean, it's kind of weird to admit, but that's what I usually do because it usually responds within 30 milliseconds. And if it starts jumping, if you're not seeing a consistency of 30 to 40 or wherever you are in the world, and it's jumping, you've probably got an issue with your connection. Obviously, if you're seeing timeouts, you should make a phone call. Run an on-flash speed test, like Speed of Me. And I only say run on-flash because I don't like to install flash, so Speed of Me is a really good one. I like that one. Run a trace route. So this one's kind of fun. I had an issue with my provider when I first moved into my house where my voice phone just was terrible. And so I called them and I was like, everything checks out. My local network's fine. My speed tests are great. And they saw no problem because like, well, your speed tests are great. You're fine. I'm like, well, that's not really the problem. It's UDP traffic that's getting interrupted. So I finally had to do a trace route. And I saw that I was going from Nashville to Bowling Green to Nashville to somewhere else in Kentucky to Nashville to Chicago. And I'm like, this doesn't make sense. There's something wrong with your routing. Like, why am I going through all these hops? And so I finally, it took me literally 4 months to get this resolved because I had to keep going up through different levels. And finally they sent a guy to my house and he's like, oh yeah, I laid these cables and they ain't the way they go. They go this way. And I'm like, okay, well great, go tell your head that. And so they fixed an issue on their router and it was fine after that. But I really had to prove it to them. So traceroute will, if you haven't done one, traceroute will tell you every link of where you're getting to your destination. So if you traceroute to Google, it'll show you every device you hit on the way. Some devices are configured to not respond to ping, so you will see timeouts. We're really not as much concerned with timeouts as we are with super high ping times. That's going to indicate where the problem is on the network. All right, so next steps. So you want to learn more about this. I really recommend the CCENT for routing and switching. It's a Cisco cert, but it's really in depth about really in depth about the history of networking and they'll talk about hubs. It's really exciting and really frame relay connections and things that are not applicable anymore. But it is a really good to understand how switching works, what to look for in packets, how to deconstruct a packet and look at all the the flags and things like that. It's a really good course and it's a gateway. It's half the CCNA if you're looking to do CCNA, and it's also a gateway even without the CCNA to other certs. So you can go from a CCENT to a CCDA or whatever you want to do next. So learn this. They'll talk about this in CCENT. They'll talk about subnetting. Don't learn it from that book. The way they explain it is terrible. I had to end up just Googling videos about how to do it because I couldn't learn from the way they were explaining it. But the reason you want to do that is because A, it makes you sound really smart, but B, it allows you to communicate more effectively with people. So you can say, I'm giving you 10.1.1, or I say the router is at 10.1.1.1/24. Well, that gives us a whole slew of information. That tells us that the network for the router is 10.1.1.0. That's the subnet that the router's on. It tells us the network mask of 255.255.255.0, and it tells us that we have 254 host IP addresses available on that subnet, all with one line. So it's a much more efficient way to communicate. And as you get into more advanced routers, and you're doing a lot of subnetting, you're going to use CIDR notation, so subnet notation like that. It's easier to type into the router, so the config file is just use CIDR. You need to understand it. Like I said, videos. Set up a lab. So the best way to learn like specifically Cisco stuff is to buy a Cisco piece of equipment, and you can get them on eBay for really cheap. Like I bought a really basic like small business, not Linksys mind you, but a small for Cisco business router. I think it was an 871, and it was like $50. And it had, the reason I picked that one is because it had switching functionality, it had routing functionality, it had some firewall functionality. So it had everything you were learning in the book, and you could try and play with it. And the Cisco gear, I sound like I work for Cisco. I really don't. I don't even really do that much with Cisco, but I'm trying to. You can, their gear is really, it lasts for a long time. It's good quality stuff, kind of get what you pay for. So you can buy something that's 7 years old on eBay for $50 and it works fine. So that was it. Thank you.